need to quickly go through calculating the energy of a charged capacitor and the energy in an inductor. We're just going to review those now before we discuss energy in electromagnetic waves. So looking at the capacitor first, to calculate the potential energy of a charged capacitor, we calculate the work required to charge it. The final charge Q and final potential difference V are related by the standard capacitor equation, which is Q equals the capacitance times the voltage across the capacitor. At an early stage of the charging process, the magnitude of net charge on either plate will reach an amount Q, written that as lowercase q. The potential difference V between the plates is then little v equals the small amount of charge divided by the capacitance. You're just rearranging this standard form. The small amount of work done for that little bit of charge, dW, required to transfer the next amount of charge, dQ, is then dWV dQ. We can replace V here, the small amount of voltage, by this term here, and we end up with the small amount of energy equals Q over C dQ. We can integrate this side now to get the total work. Then we want to sum up all these little parts here. So we sum them all up. If we integrate that, we get Q squared over 2. So the capacitor total work done going from zero charge to the fully charged state, capital Q, is simply Q squared over 2C. So that's the total energy for a fully charged capacitor. Using this equation again, we can rewrite this equation to half over QV. We can also rewrite it as a half CV squared. You can do that just by some simple algebra, doing substitutions. So you can rewrite that as all of these different ways, that way, this way and this way. Now the capacitance of a parallel plate capacitor in a vacuum, we know is from empirical measurements, is always epsilon naught, the permittivity, times the area of the plates times the distance between the plates. So that's the standard form for the capacitance of a capacitor. The electric field fills the space between the plates of volume AD. So you got this area of the plates, multiply that by the D, that gives you the volume of the area between the plates. Remember that voltage can also be written as E, the electric field, times the distance. The force per unit charge times the distance is actually the voltage. We know then that the field then is a V over D. The energy per unit volume, or the energy density U, is then, which is the energy between the plates per the volume of the plate. So that's the energy density within the capacitor between the plates. Making use of this equation here now, or rather this equation and this equation, we can express U. So if we use this and this, we can rearrange this and simply express it as U a half epsilon naught the E field squared. Now you can just manipulate some algebra that and get to that. So that basically is where we wanted to get to for a capacitor. What that says is the energy density per unit volume between the plates of a capacitor is equal to this equation. We're now going to do the same for the inductor. The reason we're doing this will become clear once we start talking about the energy in electromagnetic waves.